I'll just check because I'm messed up on this. Okay, so in y equals, you put this function, which is x cubed minus, so x cubed minus 3x squared and plus 5. So one option is you will try to plug in, because it's a continuous function, and you can use the intermediate value theorem just to see where it is. Now I know where it is, so I'm going to look at the left-hand side of the x-axis. And then you go to second and calc, and you use 0, the 0 of the function or the x-intercept. So you put 2. Oh, yes, I have a messed up. Okay. Okay, stop. Stop. It will not stop. Have to let it do its same thing, because I needed to change the viewing window. It's not going to let me do anything now. Okay, you taught me last time to go to the task manager and task. Thank you. Okay. So it's gone now. Okay. Good. I use this standard viewing window. Okay, so see the solution is right here, only one. So I will go to determine the 0 second calc. Okay, I want 2. I'm going to say between -2 and 0, and give me the 0. I didn't like it. Okay. Okay, left bound, -2, enter. I wanted -2. It's not going to give it to me because it's on the left-hand side. So I'm going to start again. I want the 0. Please behave. -2, enter, 0, enter. Yes, give me -1.1. I don't want to guess. Please. -1.1. So that's how you do it. I wanted to avoid spending the time, but if you didn't know, I wanted to show it to you, of course. Okay. So we found the X-intercept, but we couldn't. We have no algebraic tool for this yet. We have a calculus tool at the end of chapter 4, in which you will be able to approximate the solution with 15 million decimals if you want. And you will not have any difficulty solving any equation, but we have to use calculus. And we'll get to that towards the end of this chapter, in which we'll be able to solve any equation on the planet you want. Okay, so now I have to determine the limit of f of x as x approaches -infinity. As x approaches -infinity, these don't count. This dictates. These are too small. So this is the most powerful one. So as x approaches -infinity, x cubed will approach exactly. And when x approaches infinity, x cubed will approach. That's it. So I have to put -infinity here and infinity here, and I'm done with the function. There's nothing else I can learn about the function from the function itself. That's done. Now I have to discuss the first derivative. So let's continue with the first derivative. So f prime of x equals -6x plus 3x squared. Obviously, this function will not have critical numbers coming from f prime being 0, f prime being undefined, but only from f prime being 0. In descending order, 3x squared minus 6x equals 0. Factor simplify, factor simplify. Of course, I will divide both sides by 3. So I have x squared minus 2x equals 0, and I will factor out x. And it turns out that this function has two critical numbers, x equals 0 and x equals 2. I don't know if they change into anything. I have no idea. But I'm going back to my chart, and under 0 and under 2, for the first derivative, 0 and 2, under 0 and under 2, for the first derivative, I put 0. Now I go back to the first derivative, which is this. So 3 outside, x and x minus 2. And I will study the sign of this expression and put it in here. I can study the sign with a chart, or I can just plug in numbers. Let's say I plug in negative 2. Negative 2, negative, negative. Negative 2, negative 4. What is the sign? So I picked a number between this and this, like negative 2. This is negative, this is negative. What is the sign of the first derivative? Negative times negative is negative 2 times negative 4. Negative 2 times negative 4 is 8. 8 times 3 is 12. Oh, 24. Okay, now I'm going to plug in 1. 1 and negative 1. What is the sign? Negative. And finally, 10. 10 and 8. What is the sign of the first derivative to the right-hand side of 2? Do we all agree? Yes? Okay. Before I draw any conclusions about this row and this row, I don't know yet if they work in sync, but I have to determine this here. I need this point. I have this, 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 but I don't have this. So in the function that I already have in the calculator, I will go to second and table. Of course, I have to go back to the table set first. And I will plug in 2. So second and table, I want only 2. Just give me the answer. 1. So I go back and I put it in my chart. Now, since I have all the information summarized in the chart, I'm trying to see if these two work well. If they don't, I have an error somewhere. Okay. Between negative infinity and 0, what does this function do? Increase. Is the sign support? Is the trend supported by the sign of the first derivative? Good. What does the function do between 0 and 5? Is this supported by the sign of the first derivative, according to the first derivative test? Between 5 and 1, what does the function do? Is it the sign supported based on the first derivative test? What does the function do between 1 and infinity? Is it supported by the first sign of the first derivative? Now the next analysis. Very important step right now. I see that the first derivative changes sign at 0, 5. It changes sign from positive to negative. What kind of point is 0, 5? Careful. We have not gotten to the second derivative. So we can now not yet talk about inflection. So we are only talking about the first derivative, changes sign, so the slope is positive, then it's 0, then it's negative. What type of point is 0, 5? Zero, 5, local max. I see again the first derivative changing sign at the point 2, 1. It changes sign this time between negative and positive. Remember, this is what we wrote here. The first derivative test, right here. Okay? So, if it changes sign from negative slope, 0, and positive, what type of point is 2, 1? Local minimum. Very good. Now we are ready to analyze the second derivative. So I'm not going to differentiate this. I am going to differentiate this to get the second derivative, which is negative 6 plus 6x. Negative 6 plus 6x, so the second derivative equals 0. Means 6x minus 6 equals 0, which means x equals 1. Do we agree? Okay. Always leave a lot of air, as much air as, quote unquote, as you can between these points, because see, now I have to insert 1, and it has to be in the specific spot between 0 and 2. Under 1, for the second derivative, I have to write 0. And I have to put a value here. When x is 1, I go back to my chart, and I plug in, to my graph, I plug in 1, and I get 3. That point is mandatory. I need to have 3 in here. Right under 1. Exactly under 1. Okay. Now I will study the sign of the second derivative. The second derivative is 6x minus 6. It looks like this if you want to graph the second derivative. We're not going to graph the second derivative, but for the study of the sign, what is the sign of this line? It comes from and goes to, that's exactly what I'm going to write. It comes from negative, and it goes positive. This is definitely opening downward. This is definitely opening upward. The second derivative changes sign at the point 1 comma 3. What does 1 comma 3 mean? Inflection point. This is where the function will change concavity from opening downward to all of a sudden opening upward. So 1 comma 3 is inflection point. Now I would like to discuss, because I have everything I need, I would like to discuss the second derivative test. Do not change anything. I'm going to put everything back. Okay? I'm going to erase something, but I'm going to put them back. Don't change anything. Just follow with me. I have nothing against the second derivative test. I'm just using the first derivative test more than the second derivative test. But it doesn't matter. You choose. Okay. Let's say I determine the first derivative, and for whatever reason, it's easier for us, let's say, not to study the sign of the first derivative. I have not studied the sign of the first derivative. I don't know where the first derivative is positive or negative. However, I got to the second derivative, and I studied the sign of the second derivative. So I got the negative here, I got the inflection point, and I got the positive. Okay. I know that this means that it opens downward, and I know that this means that it opens upward. Now stay with me. I know that at 0, the first derivative is 0. What kind of point can this be if I know that the function opens downward and the first derivative is 0? What kind of point can 0 comma 5 be? Local max, local min, or none of the above? Of course. So if it's local max, then I know that this is positive and this must be negative, without even studying the sign of the first derivative. Now I'm here. The function opens upward, and I know that the first derivative is 0 at 2. What kind of point could 2 comma 1 be, where I know the first derivative is positive and the function opens upward? What kind of point can 2 comma 1 be? If it's minimum, then this sign has to be negative and this sign has to be positive. There is no other way. That's what the second derivative test means. I don't study the sign of the first derivative, but I wait till I finish with the second derivative. I study the sign of the second derivative. I know the concavity, and then I figure out what 0, 5 means. If the function is like this, and the first derivative is 0, 0, 5 must be a local max. If the function looks like this, and the first derivative is 0 at a point, 2, 1 must be a local min. Therefore, I figured out the signs of the first derivative. The reason why I don't like this idea, I have nothing against it, is because I need to have control. That's me. I need to have control over this line or this row and this row. If I wait till here, then I have to go back and check my numbers just to make sure I didn't make a mistake. So I don't want to wait till here to see if these two are in sync. I mean, work together well. But it's up to you. So this is the second derivative test. Let's fill it in now. The first derivative at a particular point is 0, and the second derivative is negative. So the first derivative is 0, and the second derivative is negative. What kind, at that point, f has a what? Local max. So local max has a local max. The other one, once again, this is a second derivative test. The first derivative is 0, and the second derivative is positive. Then at that point, f has a local min. Now with all this information, we are ready to graph this function with no help. We did have help in only one thing, with finding the x-intercept. But we don't need to use any help from the calculator when we get to the end of chapter 10. We will be able to get as many digits with any accuracy you want of any solution of any equation you want. Okay, since I have all the information summarized in there, here's how I start. First, I'm going to plot negative 1.1, 0. Then I'm going to plot 0, 5. Then I'm going to plot 1, 3. And then I'm going to plot 2, 1. So I have all the points. Here's my next step. Careful to try to understand this, and then you'll have absolutely no difficulties in graphing anything. Now, once again, I cannot give full credit for these graphs if you don't show all your work. It doesn't have to be in my way, your own way, but you have to show everything, all your work, step by step. So, the function starts at negative infinity, and it's increasing, opening downward till this point. Starts at negative infinity, increasing, opening downward till this point. It continues to increase till 0, 5, still opening downward. Where it has a local max. It's still opening downward and coming to an inflection point at 1, 3. At this point, it changes concavity. It's still decreasing, but now it's opening upward, going to 2, 1. See the inflection point? Opening downward and opening upward now. I didn't mean that. Okay, so I'm at 1, 3. I'm at 2, 1. Sorry. I'm at 2, 1. And now the function is increasing, opening upward towards infinity. And this is the function f of x equals x cubed minus 3x squared plus 5. All points are accounted for. And the max min, I see a local max, I see the local min, I see the inflection point. I see the concavity opening downward and opening upward. And the inflection point. I don't see how, if I have all this information on 3 pages, I'm going to be able to put it together and graph the function correctly. If I don't use some sort of summary. This one or any other that you can come up with. Any questions? Any questions? Okay, let's work on the next problem. Is the second derivative test clear? This will give us just local max, local min, like the first derivative test does. But later, after the second derivative is determined. This one gives us the first derivative test, gives us the max and the min, right after we finish the first derivative. The second derivative test, we have to wait till the second derivative to identify max min. It's up to you. Any questions? Any questions? Okay, so let's look at B. We have f of x equals x divided by 1 plus x everything squared. This is a different type of function with different needs. This is what type of function? Can anyone remind us? What type of function is x over 1 plus x squared?
Rational.
Excellent. Which means problems, asymptotes, and so on and so forth. It's not as friendly as the polynomial function was. I have to get my chart going. F prime of x, f of x, and the second derivative. Have to identify the domain. We always start with the domain. The domain of this function is say it again. Cannot be -1. If the function is undefined at -1, its derivatives will be undefined at -1. Good. I need to determine everything about the function from the function itself first. What can I find out? What about the x-intercepts? Does this function have x-intercepts? Okay, where? When is a fraction 0? Okay, when is the top 0? Good. Does this function have y-intercepts? No. If it crosses at the origin, that's also the y-intercept. I need this, 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 and this. What am I referring to here? I'm referring to the limit from x over 1 plus x everything squared when x approaches -infinity. Here I'm referring to the limit of x over 1 plus x everything squared when x approaches -1 from the left. Here I need the limit of x over 1 plus x squared as x approaches -1 from the right. Bless you. And of course here I want the limit as x approaches infinity from x over 1 plus x everything squared. Once I'm done with these 4 limits, I can start the first derivative. Can anyone tell us, let's start with the limits at infinity. Can anyone tell us what is the limit here? Which degree is higher? Good. So at infinity, what will happen? Which one will? Exactly. Absolutely. So 0 here, 0 here. What does that mean? It means that the function has a, yes, y equals 0 horizontal asymptote. Y equals 0 horizontal asymptote. I put everything in the chart, summarize everything in the chart so I don't forget anything. Very good. Now the limit on the left of -1 and the limit from the right of -1. I know it's -1 over 0. So I know it has to be an infinity. But I don't know which one. So -1 from the left with -1.1. The top is negative. The bottom, I shouldn't even discuss it. The bottom is always positive. So then negative. -1 from the right will be -0.9. I don't discuss the denominator. The numerator is negative. So both of them are negative. That's all we can determine about the function from the function itself. Done. So now I'm going to determine the first derivative. So f prime. Remember, this is a ratio. The top prime is 1 times the denominator minus the top times the denominator prime times the inner function prime, which is 1. I will factor out 1 plus x from the top. And 1 plus x I have in the denominator. I have a 1 plus x left. This is gone, minus 2x. So then the numerator becomes, after I simplify, I have -x plus 1, or -x minus 1, over 1 plus x to the third. You will see in a moment why I'm doing this. Oops, I didn't mean that at all. Okay. This is only for the sign. I don't need to do this for any other reason. Okay. So one more time, let's go back. I differentiated the numerator. I got 1 times the denominator minus the numerator times the denominator prime over the denominator squared. I saw that I have in both terms 1 plus x. I factored out 1 plus x. From here I have 1 plus x left. This is gone, it's outside, minus 2x. Then I have minus x plus 1. But minus x plus 1, I factor out -1, I have x minus 1 over 1 plus x to the third. I split this into 1 plus x squared and 1 plus x only because this quantity is always positive and I'm not going to bother with it when I determine the sign. Of course, don't cross it out like that. I'm just making a point. This is the first derivative. Okay. Now, I need to determine critical numbers. Critical numbers come from the derivative being undefined, but it's undefined at -1 where the function is undefined as well, so no critical number coming from undefined of the first derivative. But there is one critical number coming from f prime being 0. So where is this fraction 0? Only when the top is 0. And it happens that the top is 0 when x is 1. So then I go back to my chart. I put 1. I put 0 under 1 for the first derivative. I need to determine this value here. I need it for graphing. If the top is 1 and x is 1, 1 plus 1 is 2, 2 squared is 4, so this is 1/4. Now I will be studying the sign of the first derivative. I don't want to wait till the second derivative. And what if I make a mistake on the second derivative? So I'm studying the sign here. I'm going to plug in a number between negative infinity and 1, any number. Let's say negative 3. Negative 3 minus 1 is negative. Negative 3 plus 1 is negative. But there is a minus in front. 1, 2, 3. 3 negatives. I'll catch my mistakes in a minute. Now, if I wanted to plug in 0, I have 0. This doesn't count. So 0, 0, 1. Ah, okay, so I plugged in negative 10, right? So this is negative, this is negative, this is negative. Now I want to plug in 0. So this will be negative, this will be positive. Ah, see? So when I plug in 0, this is negative 1 times negative, but 0 plus 1 is 1. So it's positive, so it's positive. Okay, on the other side, 10. 10 minus 1 is positive. 10 plus 1 is positive, but there is a minus in front. It's very easy to catch our mistakes in a minute. Now, at this stage, I need to make sure that these two rows work well together. If they don't, that's the point. That's the time when I catch my mistake. Okay, ready? Okay, from 0 to negative infinity, what does this function do? I'm just looking at the numbers or the symbols here, the number and the symbol. What does it do? Is this supported by the sign of the first derivative? Between negative infinity and 0, what does the function do? Is this supported by the sign of the first derivative? Between 0 and 1/4, what does the function do? Is it supported by the sign of the first derivative? And finally, from 1/4 to 0, what does the function do? Is this supported by the sign of the first derivative? Excellent. Now I decide whether there is any max or min. This cannot be negative 1. This is undefined. Although the first derivative changes sign, but the function is not defined, it cannot be a max or a min, in this case a min. Now I move on and I see it's 0 and it changes sign from positive to negative. Positive slope, 0 slope, negative slope. What type of point is 1, 1/4? Local max. Good. There is nothing else we can learn from the derivative about the function than what we already have. Now I'm ready to move to the second derivative. Messy. Quite messy. Have to be very careful. Okay, so here's my first derivative. This is what I differentiate. I'm going to leave the negative 1 outside. I don't care for it. It can wait for me when I'm done. Negative. Top function, I don't need to put a bracket because it's going to be a fraction anyway. I'm going to delete it. I mean erase it. Okay, ready? So the top prime is 1. The top prime is 1 times the denominator. 1 plus x to the third minus the top times the denominator prime. 3 times 1 plus x to the second power, luckily times the inner function prime, which is 1, over 1 plus x to the 6th power. I'm hoping to get rid of a lot by factoring. What will I factor out? I will factor out 1 plus x to the second power. Let's see what we have left at the top. I took 2 away from here, but I still have 1. So it's 1 plus x. I took 2 away from here, but I have 3 times x with minus in front, and 3 times negative 1, negative 3 with minus in front. So now I still have minus in front, but this is negative 2x and plus 4. Very nice. Negative 2x plus 4. Of course, again, I'm going to factor out negative 1. And factor out a 2. And I like this very much. What is the sign of this? Always. Good. So I have the second derivative. Now the question is the second derivative ever 0? 1x is 2. Again, I didn't leave enough air in my table. I have to squeeze the 2 in here. Be very careful where you put it. It has to be in ascending order with everything else, of course. So now I'm studying the sign of all this. But I'm really only studying the side of x minus 2 because this is always positive. And x minus 2 is a linear function with a positive slope, just for the purpose of the sign. I'm not graphing the second derivative. What is the sign? Negative and then positive. This clearly says this. Of course, I have to plug in 2 to get this number. So it's 2 over 9. Gee, how am I going to graph 2 over 9? I don't know. What kind of point is 2 comma 2 over 9, knowing that the second derivative changes sign at that point, 2 comma 2 over 9? How do we call 2 comma 2 over 9? Thank you. That's it. We know absolutely everything about this function. So let's graph it. Oh, there is one thing that I did not write. X equals negative 1 must be a vertical asymptote because the limits left and right are negative infinity. And positive infinity, whatever, doesn't matter. As you see, I don't care for my notes on anything. I only care about the chart. Nothing else matters because I have all the information in there. So let's graph this function now. When I graph a function with asymptotes, what do I have to graph first? The asymptotes. This is an overkill. There is no need for this. Okay, so let's read our chart. The function comes from approaching the horizontal asymptote, opening down towards negative infinity on the left-hand side of the first asymptote. No question there. From approaching the horizontal asymptote, decreasing and opening downward towards negative infinity. Now, 0, 0 is this point. 1 comma 1/4. It's going to be tough. I'm going to say that, sorry, this is 1/4. And I'm going to say that this is 2 over 9. Right? This is 0.25 and this is less than 0.25. So this is 2 over 9. Okay. So the function increases from negative infinity to this point, opening downward, and continues to increase to 1 comma 1/4. Opening downward. It reaches this local maximum, which you will see it's also absolute max. And then it starts to decrease towards 2 comma 2.9, 2 over 9 right here. So it's still opening downward, decreasing till this point, where there is an inflection point, all of a sudden it changes concavity and it continues to decrease towards 0. So this is all the information that I see in the chart. So one more time, approaching 0, opening downward, decreasing towards negative infinity. Then from negative infinity, on the other side of the asymptote, increasing towards 0, 0. Continue to increase till this point, which is a local max, and in this case I see it's also an absolute max. Then it starts decreasing towards the point 2 comma 2 over 9, this one. At this point, because the second derivative changes sign, it changes concavity, and it starts opening up, but decreasing towards 0. Opening up and decreasing towards 0. So this is also absolute max, which is 1 comma 1/4. Any questions?